And we welcome next speaker, Ariel Zhitnitsky, University of British Columbia, Vancouver, telescope array bursts, and ANITA anomalous events as manifestation of the dark matter.
Okay, thank you. Can I share the screen now?
Please.
Okay, let me just. Can you see it?
Yes, yes.
Okay, very good. Okay, thank you for inviting me here to speak, and it is great pleasure to be here to see so many friends, so many faces. It's almost last time in Munich in the Axion meeting, just so many friends around. Thank you very much. Okay, let me start with the following remark. So essentially, I want to discuss about some kind of very unusual events as precisely what I have here in the title. Telescope array and ANITA, some kind of unusual events. So let me start with the following. So essentially, it's I will cover two recent papers about this topic. And the basic idea is essentially the following. So normally, when you go to different conferences, you discuss dark matter or baryogenesis in two different conferences, two different sessions. So normally it's considered to be unrelated phenomena. That one phenomena goes back to Zwicky, and another phenomena goes back to Sakharov. And essentially, my point, it is the two sides of the same coin. That's the dark matter side of the coin, and this baryogenesis side of the coin. So two sides. So, and these two phenomena normally considered as completely different. It's two completely different stories, and different people working on these two different stories. So before I go to my topics from the title, I have to explain why I believe they are actually related. And the axion field plays a key role in linking these two phenomena. So essentially, the claim is that we consider many related phenomena related to solar heating puzzle, primordial lithium puzzle, many others, and I don't want to mention all of them today. Today, I specifically discuss only two puzzles, two absolutely unbelievably interesting events, phenomena related to the telescope array and ANITA, anomalous event. So, but before I go ahead and discuss these two very interesting puzzles, let me formulate why do we believe actually that these two phenomena, dark matter and baryogenesis, are actually linked and one and the same phenomena. So normally people say dark matter must be actually a new field, such as WIMPs. Well, where does it come from? Normally it comes that it must be non-baryonic, it comes from Big Bang nucleosynthesis, it must be decoupled from dark matter radiation and stuff like that. So essentially what we are saying that instead of new fields, we are suggesting new phases of old fields, quarks and gluons. About baryogenesis, instead of creation of baryons, we are talking about segregation or separation of charges. So the idea that dark matter could be in form of a conventional standard model particles has been known for years. So essentially, Witten discussed in 1984. And for cosmology, the crucial point that it is not just the new field with a very weak coupling constant. The crucial point for cosmology and astrophysics that it is essentially this ratio, cross-section and mass must be much smaller than one than for conventional hadronic phases. So just Witten discusses in 1984, and it was actually short-lived. story because of a number of reasons. First of all, you need a first order phase transition. People discuss fast evaporation. It's very hard to achieve stability in a QCD, which we know. So the new portion, my contribution here, that essentially the axion rescue to this idea, and we call this object axion quark nuggets. So in future, I will talk AQN. So, and the idea is the following. Once you have the axion, in this case, you have so-called n equals 1 axion domain walls. So no matter you like it or you don't, you always have such kind of objects. And in this case, you don't need a first order phase transition. And the second part that essentially you have, which is different from the conventional Witten's idea, that you have not only nuggets, you have anti-nuggets as well. And small geometrical factor always will be present in the system because it is not just normal atomic matter, it is a nuclear matter. And for nuclear matter, you can easily compute this ratio. And if the object is sufficiently large, it is related to the charge of baryons, which is hidden in the nugget. And if baryon charge is large, let's say 10 to 25, in this case, this number is really very, very small. So why, historically, the reason why I push this idea forward, that essentially main goal was that we have definitely visible matter, which is proportional to the proton mass, has nothing to do to the Higgs, has nothing to do to any actually quark mass. It is a proton mass which is related to the lambda QCD. And in this case, there is only one single dimensional parameter in the system. It is a lambda QCD. And in this case, dark and visible density are always order of 1 and does not depend on the initial theta. It does not depend on the axion mass. It is a very generic feature. Okay, so it just the way how it looks like, that there is an axion domain wall pressure. It is a Fermi pressure, and that's the most important part for me for now. Now, because Igor is around, in this case, I want to show this slide as well, very, very short, that there is a generic misconception that the topological defects, such as domain walls, can be only formed if Peachy Queen transition occurs after the inflation. That's where people did the most of the simulations, numerical simulations. But the point is that n equals 1 domain walls interpolate between topologically distinct but physically identical vacuum states, like in Sine-Gordon model. And in Sine-Gordon model, soliton interpolates between theta and 2 pi, which is a physically identically the same state. So, and horizon definitely must accommodate both, all of them, all these topologically different states, okay? So essentially, n equals 1 axion domain walls always exist, no matter what theta, because theta interpolates between theta and 2 pi. Okay, so now I come to the most important part for me for today. So first, let me explain what the telescope array bursts are. So they published a paper, and what they observed some kind of very unusual events. What these unusual events are? So there is unusual features. The first one, clustering puzzle. So essentially the way how these events were selected, that they consider 3 plus events within 1 millisecond, and if you consider as a normal cosmic rays, in this case, it would be extremely unlikely to have such kind of events in the same area, 1 kilometer area. Because if you try to feed the observed burst with a conventional code, in this case, you have to have cosmic rays energy on the level 10 to 13, but intensity suggests that it is in the level 10 to 19. That's the first puzzle. Another puzzle, I'll show some kind of plots in a second. So the curvature puzzle. So all bursts are much more curved and very unusual so-called H puzzle. I'll show again what is a H puzzle. And synchronization puzzle. Again, it's extremely unlikely that thunderstorm somehow changes the property of the cosmic rays. It's very, very hard to imagine how it could happen because you don't have such kind of energies. Important part that essentially some bursts are not related to lightnings. They actually always occur when you have a thunderstorm system, but actually lightnings is not there. So 3 of them out of 10. And the total number of 10 bursts during the 5 years of observations. Okay, now let me show what do I mean by saying some kind of unusual events. This is a curvature puzzle, and typical burst event, you see that this is a curvature, which is a very, very different curvature from the typical event. And this is a H puzzle. So the typical cosmic ray event is just very, very sharp peak here. And at the same time, typical burst event is very, very wide. So it's something like 10 milliseconds width, but nevertheless, it's very different from this one. Now, and it was a journalist who published a story about my paper, but with a telescope array about axion quark nuggets, but I better actually explain and show a few slides what the physics is about. The way how I see it. So essentially, the basic idea is the following. The nugget propagates in atmosphere. And because it has so many anti-nuggets, that's important, so many annihilations, in this case, internal temperature of the nugget could be huge, up to 10 keV, could be even larger. Now, once you have a temperature, in this case, you have a huge ionization. Once you have a huge ionization and you are in the system with a large electric field, which is a typical field in the thunderstorm area, in this case, what's happening that some positrons actually can be liberated. And in this thunderstorm field, which is known to exist with correlation scale on the level of 100 meters, so-called avalanche scale. In this case, these positrons can be easily accelerated to 10 MeV energy. Important part that once you have such kind of energy, in this case, the mean free path is huge. It's kilometer scale. Okay, so let me show a couple of formula. What is the typical electric field which must exist in thunderstorm for so-called runaway breakdown. That's some kind of theory which is considered as a conventional for lightning events to occur. So that's the typical estimation for the typical critical field. It definitely depends on altitude. That's typical avalanche scale. That's typical time scale. Now, once you have such kind of environment in this case, and you have ionization, again, the formula have been derived long ago for the density, so-called electrosphere in these nuggets. We can estimate the charge of the positrons, and we can estimate so-called radius, capture radius, where positrons normally reside without electric field. But once you have electric field, in this case, you definitely can easily liberate such kind of charged particles because binding is not very, very strong. And the energy for particle which exit the system, thunderstorm system, it's about 10 MeV. Now, let's try to compute the total number of positrons which can reach the telescope array detector. So that's 1 over r, it's how far away you are. That's the number of detectors, that's the size of the detectors. So it's about 10 to 3. about 1,000, which is about the correct number people observed for the particle. So let me explain the way how they are distributed. So this parameter for distribution is related to the internal temperature in the nugget. And in this case, there is a spatial distribution and there is a temporary distribution because the path is a little bit longer. So again, it is a pure geometry to estimate these parameters. And the point is that it essentially, indeed, it's a typical 1 kilometer scale. And indeed, it is a typically millisecond scale for the spreading in time of and spatial direction. So what it means that time spreading and spatial spreading, when it is changes on the level up to 8 microseconds. In this case, the changes here up to 2 kilometers, and that's exactly the curvature puzzle. That's exactly up to 2 kilometers, you can see here, and that's up to 7-8 microsecond, which is a very, very different from conventional cosmic ray events. So again, synchronization puzzle. Synchronization becomes really a puzzle when you consider all these events as absolutely independent events, random events. But here it is not random events, they're actually clustering events. And this cluster is one and the same axion quark nugget because it is non-relativistic velocity. It traverses very, very short distance on the level of 0.2 kilometers during all this millisecond scale. So essentially, it is a cluster of events. It is not random events. And that's exactly the explanation of this clustering puzzle. And about H puzzle, again, it has a just a very simple explanation because it is a number of electrons produced during the same time. And you have large number of them approximately with the same velocity. You do not expect very sharp H as you normally expect for cosmic rays. And indeed, you see that very, very broad distribution instead of big distribution. That's resolution of the H puzzle. So essentially, we suggested how this proposal can be tested. And the way how we suggested this proposal can be tested, that if you increase a little bit, because 1 millisecond, it comes from nowhere. If you increase time for the burst, in this case, definitely you would expect not only 3, you should expect 3, 4, 5, 6 different events. It would be our prediction. And also, it must be a radio signal which is synchronized with this burst. So we did the computations for the radio signal, and typical bandwidth for this radio signal, it's in this range between 1 and 200 megahertz. And typical amplitude on the level 20 millivolt per meter, and a duration on the level 0.3 microsecond. And all these parameters are actually coming from these pictures. They are not related to lightnings or cosmic rays physics. Okay, and now I'm coming to another anomalous events, which is ANITA anomalous event. And I take all questions about telescope array events at the very end of the talk, because just I don't want to have to be interrupted right now. So again, extremely unusual events. Let me explain these unusual events. 2 events, very, very hard to explain. So, and let me explain the problem. I'll show the slide. Maybe I'll show the slide here. So essentially, when they have very, very large angle here, and that's exactly what they observed, it means that some kind of particle must travel very, very long distance inside of Earth in the interior. So essentially, they observed 2 events with very, very large angle, 27 and 35 degrees. And if you say, well, we have neutrinos which can travel a very, very long distance, so it could be neutrino, but the problem with the conventional standard model neutrino is the following, that essentially it must be very, very large energy to match the intensity ANITA observed. And such kind of energetic neutrino cannot travel very, very long distance. So the standard model neutrino is actually excluded. Okay, so that's exactly the problem. That's very, very large angles has not been expected from the very beginning, but very small angles had been expected because altitude it's about 35 kilometers, so it is definitely not at scale. This is a 6,400 kilometers, but nevertheless, if you have a little bit above horizon cosmic rays. In this case, you have indeed polarity, which you would expect from such kind of traveling. But nevertheless, that's a 27 degree. It's very, very large angle. So let me show a couple of plots related to the ANITA observations. So that's non-inverted polarity. That's exactly anomalous event. That's, you see precisely the way how non-inverted polarity is with a minus 35 degree. So such kind of events had been observed, but for 5 degree or 3 degree, that's two different events. It is a non-inverted polarity. But all normal cosmic ray events, which actually due to the reflection, for example, with this huge angle, they have different polarity because it is a reflected and the electric field is reflected. So that's exactly what they observed. Now, again, it is a journalist paper about these anomalous events. They use such kind of terms, oddballs, new physics, but I want to show my understanding what is actually happening as a AQN events. So once maggot travels for a long period of time, just something like 30 seconds in the Earth's interior, in this case, it is extremely hot temperature. It's on the level estimation 200, between 1 and 200 keV. So the point is that in this case, E plus and minus production becomes actually possible because the suppression is still there, but it is not dramatic, which you normally expect. And you do have electric field and electrosphere in nuggets, just because of the ionization I already mentioned. And if you produce such kind of positrons, in this case, the normal positrons experience attraction, so they go to their Fermi surface. It's their place. But electrons now, they can actually exit the system. And again, typical energy at the exit on the level 10 MeV. Okay, so, and that's a bunch of electrons emitted at the same instant from the same location with very, very high energy, and they produce a coherent radio pulse in the background of the geomagnetic field. That's exactly the main point, the main idea, where the radio pulse, where does it come from? Now, about intensity and about the numbers. Normally, when you have a cosmic ray with energy 10 to 17 to 10 to 18 eV, normally you expect number of charged particles, normally electrons, positrons, on the level 10 to 8, 10 to 9. So it is estimated that number of electrons in a bunch which can leave the system on the same level. So what it means that the AQN-induced and cosmic ray-induced radio signals are similar in intensity. And once you actually know, once you estimated this number, in this case, you say, well, now I go ahead and compute conventional electric field at a distance and all other parameters. So you use conventional formula from Jackson or from Landau-Lifshitz, and you estimate the basic features of the pulse. So there is, as always, critical frequency, which is on the level 0.7 gigahertz, and you estimate typical duration of the signal, which is on the level few nanoseconds, and you estimate typical intensity of the pulse, which is on the level millivolt per meter, and you estimate typical power density, which is on the level 0.2, 0.3 picowatt meter square megahertz. So, and all these values are very, very close to the observed magnitudes. As I said, that the parameters here are from completely different stories, but nevertheless, they match parameters of the observations quite well. So let me show just our plot for electric field, which is measured by ANITA. So in units millivolt meter. So it's roughly speaking 1, 2 millivolt meter. And filter which we use the filter which ANITA uses. And depending on gamma 10 or 20, you have a little bit different pulses. But all parameters in terms of nanoseconds, in terms of the intensity, it's about right. So now, I want to comment here that there are dramatic differences with the conventional cosmic ray radio pulses between AQN induced and cosmic ray induced, and it can be easily discriminated. So let me explain the difference. So normally when you discuss about cosmic rays, they are characterized by so-called central axes. They have a shape of the pancake geometry, and such kind of notions simply do not exist in our scenario. For example, the width of the pancake normally, so again it is some kind of simulations, it grows with a distance from the central axis in extended air showers. And in this case, it is dramatically modified the spectrum and intensity of the emission, because at some point the wavelengths becomes shorter than the width, and in this case coherence of these particles diminishes. So it's very, very sensitive to the pancake width. In our case, it is not the case. In our case, because the width, it's roughly speaking the same, and it does not depend on the distance from central axis. So, and therefore the pulse is different. So now I'm about to conclude, and conclusion is the following: that essentially, normally when we say it must be non-baryonic dark matter, it could be ordinary baryonic dark matter we know and love, which is simply an exotic color superconducting phase. And we coined this model as axion quark nugget dark matter. In this case, the ratio, which was actually the motivation for this model to push forward, that the ratio between dark and visible is very generic consequence. Does not depend on the axion mass, does not depend on the misalignment angle, because there is a one single scale in the problem. It is a lambda QCD. There is no any other scales in this problem. And this model sorry, offers a number of different resolutions related to the biogenesis. I didn't discuss solar corona mystery, but again, it's very interesting. I didn't discuss lithium problem. I didn't discuss many other problems. I discussed just two, telescope array and ANITA, and I'll show the way how it works, because there are actually antimatter and intensity could be huge. Now, let me show, it's not my last slide, but a number of different or related problems. And I have just only three: telescope array, ANITA, and dark matter. And these three term from my title. And I didn't discuss anything else. Okay, now I want to show a slide actually from Dietmar Butker in the Axion meeting and the previous Axion meetings. And his view was that essentially matter antimatter, it is a one elephant in the room. There is a dark matter and similarity between visible and dark matter. It is another elephant in the room. The dark energy is the third elephant in the room. And he put many different elephants in the same room. So my view is very different. That essentially we are talking about one and the same elephant in the room. And different people from different fields conducting different experiments around the globe, in fact, observe one and the same elephant that study different parts of the same body of the same elephant. So I want to conclude with this slide. So essentially, we are talking about one phenomenon, one very unusual phenomenon. Okay, thank you.
Thank you, Ariel. Very interesting proposal. Any questions? Sergey, please.
Hello, thank you. Thank you, Ariel, for this very nice and intriguing talk. May I ask you to show the slide about possible future tests with telescope array?
Possible future for telescope array. Let me just go ahead and find it quickly. Okay, so here it is.
Thank you very much. My question is, suppose we can perform all these tests, which I don't think that is not realistic. What at the same time, there exist some explanations related to atmospheric electricity and all that of these events. What is how? Okay, we measure something. You measure some numbers, yeah, and we find some signal which is roughly in this bandwidth and amplitude, or maybe just close to that, but not precisely, and so on. Do you have some distinctive prediction which can distinctive observation which can result in saying, all right, this is for sure not axion quark nuggets, or this is for sure not conventional atmospheric electricity explanation? Of course, it is not just the usual cosmic ray, but what shall we measure to separate definitely your proposal from some atmospheric electricity based things?
Okay, so essentially, the point is the following. When you have a conventional electricity explanation, you might remember that all the events, all the bursts occur before actual light flash, lightning, or lightning might not even occur, but nevertheless, you do have such kind of phenomena. So it is definitely cannot be related with the lightning, because you have three events which are not related to the lightning at all. So it must be related to some kind of electric field in the thunderstorm, not exactly with the lightning. And my main point here is the following: that if instead of this delta t 1 millisecond, which you normally have, if you increase, in this case, you do not expect to receive, instead of 3 consecutive events, you do not expect to have 4, 5, 6, and even more. And I do expect here, because the nugget is very slow moving object, so it remains in the thunderstorm for a long time. So it produces more and more events. And you might remember from the telescope array that essentially you had seen a number of events which is very similar to this, with very unusual features, which edge puzzle and stuff like that. But nevertheless, it was only one single event. But what I'm saying that if you have instead of delta t instead of 1 millisecond, you have 2, 3, 4. In this case, the number of clustering events become larger and larger. So that's one prediction. Another prediction which has not been done is the following. It is a radio pulse. Radio pulse, it's known to exist during the thunderstorms. It has been measured, it has been observed, and mostly it is related to the lightning. But when it occurs, it normally occurs during the lightning event and during when lightning is already actually in a late stages, not at the very beginning. So essentially the point is the following, that if you observe the radio signal even before lightning occurs, or even without lightning, but nevertheless you have some kind of radio pulse, which is precisely occur at the same time when you have such kind of mysterious events. In this case, it cannot be because of the conventional atmospheric phenomena, because lightning, after all, may not occur at all, because you had actually 3 events without lightning. So that's the main ideas. I am not talking about specific numbers, because specific numbers could be slightly different, but never similar, but slightly different. But there are some kind of very qualitative, distinctive features between these events and, for example, radio signal during the lightning events. During the lightning events, radio signals always occur, but they occur during the late stages. But here you would expect that it is actually in the early stages when actually mysterious events occur. And all events, telescope array events, occur actually in the very beginning of the lightning, before the lightning occur, or even without lightning. So that's the difference. So if you have a single event, radio synchronized event, when there is no lightning whatsoever, you cannot explain such kind of radio pulse using conventional atmospheric phenomena. Does not exist.
Thank you.
Question from Igor. Igor, please.
It's not question, it's rather remark. Eric, I counted 5 members of Telescope Array listening to your talk, and I think we have a lot of questions.
Okay.
And
we can have a Zoom meeting actually at any time when it is convenient for you and me without a conference.
Your presentation is very compressed, and so on every slide we have tons of questions, but it might be interesting to look at, and I think we should have a Zoom meeting, but not now. In a couple of weeks there will be, in July, the whole July will be ICRC conference.
Igor, very good.
After
so essentially,
August or September.
Very good. I am free man. I am not teaching now. So it is a much more actually hard for you to collect 5 experimentalists at the same time. You have a real job to do. So essentially I am available for sure.
Okay.
Oh, that's nice suggestion. I support it personally. A question from Zurab, please.
Okay.
Zurab, I cannot see you. I want to see you, Zurab.
I have to switch also my video.
Okay, Zurab, hi.
So, how are you? Nice talk and very compressed though, but I have a very simple question. First was whether Auger experiment has seen also something similar.
Which one?
Auger experiment.
I didn't know that.
Because they have bigger time of exposition and bigger area and so on.
you know, I know about other experiments, and I'm about to
Or
actually
HIRES or something like that, which was pre-telescope array.
because I know some other experiments such as Horizon 10 in Kazakhstan. They observe some kind of unusual events, and I'm working on that, and I believe it is related to what I'm talking about here, about Horizon 10, but I didn't know about OGE.
Okay. And the second was simple question.
We have to discuss this later. Maybe we can actually look carefully, and you let me know precisely.
OGE surely did not publish anything similar for that assignment.
Okay, how do I know in this case?
No, but okay, but maybe you have first thing to test whether they have also some events which they simply throw somewhere in the basket, right? And another, what you assume about the velocity of these nuggets?
Okay, it is a conventional dark matter velocity. It's 10 to minus 3 C. So the conventional, the nuggets themselves, it is a conventional dark matter. So they just have galactic velocities.
No, okay.
We assume that they have a conventional stuff like that. It could be it has not been worked out, but it could be the case. Essentially, it's Konstantin Zoitas is pushing me on this direction, that because they are not elementary particles, in this case, when they interact with the Earth, they interact with the other planets or stars. In this case, essentially conventional standard halo model may not be actually the case. It could be a little bit different, and dark matter density locally could be a little bit different. But I don't want to speculate on that right now.
Okay.
Peter, please, your question.
Okay. Yeah. Well,
Hi, Peter.
Hi. I'm not an atmospheric physicist, but we just had a collaboration meeting. In particular, we have heard a talk of Rasha Abasi, who is studying in the collaboration this lightning events and their interpretation. And from that talk, I've got an impression that it's not at all unusual for atmospheric physicists to have sort of intercloud lightning which is not seen, which is not registered as lightning, which happens, I don't know, cloud to cloud shortcut, something like that. Well, you have put a lot of emphasis on this events which are not accompanied by registered lightning, but did you ever look in any detail of how unusual they actually are?
Yeah, essentially, I look at the literature about atmospheric phenomena, and I look at the radio signals, and it is very, very different. It is definitely they do not have these features in terms of the what actually telescope array registered. They do not have such kind of H puzzle. So let me show such kind of phenomena. They don't have this phenomena. They don't have such kind of phenomena which again telescope array observed. And again, the reason why we wrote a paper about the radio signal, again, they observe completely different radio pulses, which are not radio pulses we expect here. That's exactly the reason why I want to actually see experiment, measure the radio pulse related to synchronized with the telescope array, and it would be definitely a very distinctive feature from the conventional atmospheric phenomena. Very distinctive. Features are very different.
Okay, thanks.
So in terms of the frequency, in terms of the electric field, so just all these features are very, very different. And most important part, the synchronization. When you, for example, see the following, you have some kind of pulse synchronized just before the lightning. In this case, normally radio pulse comes from the lightning, and they know that. But essentially, when you have you have seen something before the lightning, it cannot come from the lightning, and it does not come from the later stages of the lightning. And it can be attributed to the conventional atmospheric phenomena because it is synchronized differently with a different phenomena.
I'd say my question was a little bit different because it can happen that telescope array observes an event like that, very unusual, just as you say, but the atmosphere monitoring system just don't register a lightning, even if the lightning has happened.
Yeah, that's true, but radio signal always can be observed. Even if you don't have lightning on Earth and it is not recorded, but nevertheless, radio signals are recorded all the time.
It's recorded in different frequencies, and the one we were using in the paper you mentioned use one frequency range, and now we have installed another radio detector for lightnings at telescope array. So if we include the results of the newer radio detector, we may get more information about different types of lightning charges, and we detect more lightning than NLDN, which was cited in the paper, is the first paper you mentioned. Therefore, many things to discuss about the prediction, I think.
Okay, so essentially it's very different frequency bands which are normally discussed with the conventional atmospheric phenomena. But it is definitely complicated physics, and I am also not expert in atmospheric physics. And the only what I do, I just look at the literature on atmospheric phenomena, and I definitely see that the pulses have different frequency bands, they have a different time duration, so features are different. And I agree that it could be some kind of lightning which is not recorded because it is a cloud to cloud. But nevertheless, if you actually see synchronization, which is with a lightning, which did occur, but before this lightning, it is definitely very, very different from lightning you didn't occur, yeah, which is didn't record.
Well,
So synchronization plays a key role here.
We have to continue with the program of the workshop. Thank you, Ariel, for giving a concrete predictions, because it's great to see that you have a real predictions. Each of them may be a separate study, which we may discuss. Thank you.
Okay, thank you very much.
That